One of the most important concepts in economics is that of utility maximization. And in that, we assume that the way people maximize their overall happiness is that there are two completely different things going on. And then how those two different worlds merge is what goes into that decision. One of those two things is what can you afford? And that's based on what are the different prices of different goods and how much money do I have. And that whole thing is basically called your budget constraint or your budget line. So on the one hand, you have what can you afford, regardless of what I actually like, and then separately, completely independent of your income and the prices in the world, is what do I actually like? Do I like apples more or oranges more, or what combination gives me what levels of happiness? And so based on a combination of what you want to ideally do versus where your budget constraint comes in, is the boundary of those two worlds is essentially how you decide what decision you're optimally going to make for what you end up buying and how much of each good you end up buying. So let's talk about each one individually first and then merge them at the end. So the first of those things is called the budget line. And it's called a line because essentially the way we represent it graphically is in y equals mx plus b format. Now, any budget line is written in this format. Any budget constraint is in this format. Let's take a look at this. Here, P1 is the price of the first good. So here, imagine that you're basically considering how much of each of two goods to buy. So let's just say, for simplicity, the two goods in question are apples and bananas. And let's say that you're calling X1 apples and X2 bananas. Then here, P1 is essentially the price of an apple, and X1 is how many apples you choose to buy. So therefore, the product of those two things, P1 times X1, if I buy 10 apples for $2 a piece, 10 times 2 is going to be 20. So that product gives me how many total dollars I spent on that good. And then P2X2 is how many total dollars I spent on the other good, right? It's the price of each banana, and this is the number of bananas that I bought. And so those two add up to how much total money I'm spending on apples and bananas combined. And so here, assuming that there's no such thing as savings and there's no third good in the world, and that you have M total dollars and you have to spend those on either one of these two goods. So within that world, for the M dollars that you have to spend on those two, well then your total expenditure on apples plus bananas adds up to M, right? So that fundamental thing is your budget constraint, your budget line. And usually the way we graph this budget line is that we put the second good, X2, on the y-axis, and the first good, X1, on the x-axis. Philosophically, it doesn't matter which good is on which axis, but it's all about being consistent. Once you've decided to call this good X1 and that good X2, then everything you interpret, the slope and the ratios and all that, has to be in that mindset. So philosophically, it doesn't matter, but just be consistent. So now, long story short, when you end up graphing this line, it has a negative slope. The reason it has a negative slope is basically because if you want to have more apples, then you'll have less money to spend on bananas, and so therefore you're going to end up buying a lesser quantity of X2 of bananas. And so the more of one good you have, the less of the other good you have. Specifically, the slope of this budget line is always negative P1 over P2. It's always negative the price ratio. Now, we could look at a very specific example and you could see that works out. And we can also see generically why it has to be exactly that. So let's just do a very specific example first. Let's say I just gave you that apples are, $2 each, and P2, this other good is, $4 each. Then this equation is essentially 2x1 plus 4x2. And let's say your income is just, the total money that you're spending on them is 100. So with this budget constraint setup, if you wanted to plot this mx plus b, where this is your y, you just have to solve for x2. So the way you're going to do that is you're going to subtract 2x1 from both sides, so you get 4x2 equals minus 2x1, right? You subtract that from both sides, and you have this 100 here still. Then divide both sides by 4, and you get x2 equals negative 2 over 4, which you could simplify to 1/2 if you want, x1 plus 25. So this budget line, notice the slope on it is negative 1 over 2, and that's the exact ratio of P1 to P2. 2 over 4 is 1/2, and negative because it's a downward slope. And so again, that's not just a coincidence, and here's why. Let's look more generically here. If we were the first economists ever and we wanted to solve for x2 in this P1x1 plus P2x2 equals m, if we wanted to solve for this x2, just generically write an mx plus b for that, we would subtract this P1x1, so we get P2x2 equals negative P1x1 plus your money, and then divide both sides by P2, and you get x2 equals, divide each of these by P2, so you get negative P1 over P2 times your variable x1, and then plus m over P2. So looking at this equation, now it's pretty clear that the slope here is negative of the price ratio, and that's sort of why. And the reason it's important to know that is because then you can sort of see what happens to this budget line when one of the prices changes. So here, if I were to just tell you that all else equal, the first good becomes more expensive, well then, that's saying that this line is going to get steeper. So if the first good gets more expensive, it's going to get steeper. But if the second good gets more expensive, well now, the slope's going to be closer to 0, because it's a bigger denominator, so it's going to get flatter. And other way around, if the first good becomes cheaper, it gets flatter, and so on. So that's just something to keep in mind. And again, this will come in, the more economics you study, that'll help you visualize things like income effect and substitution effect when your budget line pivots, things like that. But here for now, just knowing that the prices, the ratio of the two prices is what determines that slope, and then thinking about how the prices change the tilt of the slope is going to come in handy the more economics you study. Similarly, here, looking at this m over P2, that kind of makes sense, because what this is saying, this is the y-intercept. That's this point over here. What that's saying is, if I choose an x1 value of 0, if I just choose, I don't like apples, I'm not going to buy apples at all, then what this is giving me is how many bananas I'll be able to buy, right? If I allocated all of my money on just good number 2, and set my x1 equal to 0, how much of good 2 can I afford? Well, let's think about it. Just logically, without even doing any math, you'd say, all right, if I have $100 to spend, and if the second good costs P2, well then $100 divided by P2 is the amount of it that I'll be able to afford, right? If bananas are $2 a piece, and I have $100, I'll be able to buy 50 bananas. So that's all that is. That's what m over P2, your money divided by the price of each unit, m over P2 is the y-intercept. And similarly, this x-intercept is going to be m over P1. That's if you spend all your money on the first good. And so now you can see all else equal, if I just said the prices stay the same, but that your income goes up, well now this budget line is just going to shift out in a parallel way because the price ratio isn't changing. On the other hand, if I said that both goods become half as cheap or something, then the price ratio is still not changing. So that's also, that's the same thing. Basically, both goods having their price cut in half is mathematically the same thing as your income doubling, because that's basically going to keep the slope the same, and it's just going to double both these intercepts, right? On the other hand, if I just said that the price of both of these doubles, then that's just going to shift it totally inwards like this, because both of these intercepts get half as big. But again, if both of them are doubling, the top and the bottom, then the price ratio is not changing at all. Now, here, if I just tell you that one of these two goods doubles, if I just say that good 1 becomes twice as expensive, but not good 2, well then your budget constraint will sort of tilt in like this, where now this is like a much bigger, twice as much of a denominator, so this is like half as much as it was originally, but this is the same, so it's now again twice as steep, but this intercept still hasn't changed. Now, a couple other final notes on budget constraints. You don't necessarily need to have a budget constraint that's about money. You could have a budget constraint about a different concept, like let's say you want to consume exactly 2,000 calories, and you're choosing between two goods, or like lunch and dinner, for example, and you're wondering, or not lunch and dinner, but like how much of this one good 1 to have versus good 2 to have, and each has a certain calorie amount. So let's say good 1, which we can call x1, has 300 calories in each unit of it, and good 2, let's say, has 500 calories in each unit of it, and you want to consume exactly 2,000 calories. Well, then the budget constraint is going to be 300x1 plus 500x2 equals 2,000. It's like you have $2,000 to spend, right? Calories to distribute between these two. And again, the product 300 times x1 is the total calories on good 1. So if good 1 is slices of pizza and each one is 300 calories, then 300 times the number of slices of pizza is the total calories on pizza plus the total calories on breadsticks or something, and that equals your total calories. There's nothing about this this equation generically that says it only has to be 2 goods. You could have a third good, and then it's just literally, you could extend it. If there's like a lot of goods, it's just P1x1 plus P2x2 plus P3x3, right? So this could be, you could have as many goods as you want, add them all up, equals your total budget on all of them combined. But of course, in that case, graphically, you can only really graph any 2 of them at a time, because we live in 2-dimensional space. So that's really all you need to know when you're getting started about budget constraints and how the math goes into that. And now, speaking of having too many variables to graph things, let's now turn our attention over to the other concept here in economics, which is utility. So again, on the one hand, you have, what you can afford based on the prices in the world and your income. And completely unrelated to that, you have what you prefer. So like Jeff Bezos and I, we have wildly different incomes, M, to spend on the goods, but that doesn't go at all into determining what our utility would be. Because the utility is just saying, if prices and income were not a thing, what actually just gives you just pure pleasure from consumption. And so essentially, if you have a utility function, so this is an example of a utility function, that your happiness is just the number of apples multiplied by the number of bananas, and that's basically giving you a utility level, and that's going to then somehow go into your happiness. And so in order to maximize your sort of happiness given your constraints, the thing that we do is we end up maximizing this function subject to a budget constraint. So mathematically, to solve for this, we would use calculus. We would use the budget constraint from earlier, swap out for one of these two, and figure out what combination of apples and bananas we would need to buy to maximize this happiness level of ours. But how do we try to graph this alone? So budget constraint aside, how do we graph this in 2-dimensional space when there's 3 letters here, U, X1, and X2, and they're all kind of variables here. And the way a mathematician would do this is what we call a level curve. So it's called a level curve in pure mathematics, and specifically applied to the context of economics and utility, it's called an indifference curve. So an indifference curve is essentially, so here's what this is. It's saying that suppose your utility value is fixed. So instead of all this being a variable, you're just saying, all right, let's look at all combinations of apples and bananas that give me exactly, let's say, 25 units of happiness. And then all such combinations is called an indifference curve because you're indifferent between all of those bundles. So now, going to the graph here, if this is x1 and this is x2, so again, this is the number of apples, this is the number of bananas, any point on this plane is what we call a bundle because it's a certain number of apples and a certain number of bananas. So imagine it's like a basket with a certain number of bananas and a certain number of apples. And so if you have the point 4, 1, then that's 4 apples and 1 banana, and so on. So let's say I were to say draw the indifference curve specifically for a utility level of 25. So notice, if I were to just say draw the indifference curve, that's an ambiguous question. There's infinitely many indifference curves, one for each level of utility. So if I just first say, all right, I'm going to set utility equal to 25 and see what happens. So let's think about it. So if this is 1, then x2 would have to be 25 in order for their product to be 25. So 1 comma 25 is a point on my indifference curve. If x was 5, then this would be 5, right? 5 comma 5 is a point on my indifference curve. If this was 10, then this is like 2.5, right? Whatever 25 divided by 10 is, and so on. If this was 25, this would be 1. If this was 50, this would be a half. 50 times a half is 25, right? So long story short, in this example, it sort of looks like this. It's getting closer and closer to 0, but won't quite hit there. And so that's called an indifference curve, an IC. But specifically, it's the indifference curve for 25 utils of utility, right? Now, that's just one. I could then ask you, what's the indifference curve for a utility level of 100? Well, then you're looking at all XY combos that multiply to be 100, and then that's going to be like higher than this. And so that's the indifference curve for utility level of 100. And there's infinitely many. There's like infinitely many in between these, right? It doesn't even need to be a whole number necessarily. You could have, what are all the values of x1 and x2 that multiply to give you a utility of 26.3 or whatever, right? In general, the equation of this indifference curve, let's see. Usually this is the notation that is common in econ textbooks, is they'll say, all right, let's set utility equal to a fixed value of utility. And they usually call that fixed value of utility U bar. So U with the bar on top of it, not to be confused with mean or the average in stats, is really just the a fixed value for utility that you can choose. So if that's equal to x1, x2, in order to graph this with x2 as your output variable, you want x2 by itself on one side. So I would just divide x1 on both sides, and I get u bar over x1 equals x2. So long story short, this is an equation. And so for the indifference curve. So if I were to say, what's the equation for the indifference curve at a utility level of 25, you would say x2 equals, let's see, u bar over x1. So that's just going to be 25 over x1. So now it's pretty clear. Here you could plug in a value for x1 and it'll give you, so if x1 is 1, x2 should be 25 over 1, which is 25. That's where this point was. If x2 is 5, then if x1 is 5, then x2 is 25 over 5, which is 5. So that's why the 0.5 comma 5 is there, and so on. But if utility level was 100, then this is like 100 over, and then whatever your x1 is. So for all possible values of x1, you could then figure out what your x2 would have to be. Now, because all of these combinations give you the exact same level of happiness, the exact same level of utility, you're basically indifferent. If I were to ask you to choose, what would you rather have, bundle A, bundle B, or bundle C? You'd say literally either one. I don't care. They're all the same to me. I'm indifferent between them because they all give me the same U level, which is U bar, whatever I chose for that indifference curve. And that's why, because you're indifferent between all the bundles on it, it's called an indifference curve. It's a set of all bundles that you're indifferent between. And again, there's many such sets. So this is one set at 25. There's another set. All those bundles give you a utility level of 100. If I were to ask you to choose, though, between point D and point A, here, it's pretty clear that you want D because it's on a higher indifference curve. In general, we want to be on as high an indifference curve as possible because that's giving us the most utility. So finally, in general, so how then this interacts with what we talked about earlier, the budget constraint, is this. It's that we basically have, let me just write this out here. We basically have two things going on. One is there's a set of things that we can afford. That's our budget line, right? I'm just going to make this a different color. So this is our budget line. Budget. And so we can afford anything on this line. Technically, we could also afford things below it, like a lower value of x1 and x2, but that's not using our full M dollars available. So really, if we want to use exactly the M dollars, we have to purchase something on this red line. And here, that said, there's many different indifference curves that might look something like this. And essentially, we want to pick what's the highest of these blue curves that we can be on while still being on our budget constraints. So you could pick this point, for example, right? That's a point. It's on the red line, meaning you're spending your full M dollars, and it's giving you utility. Let's say the utility there is 30. It's giving you 30 utils of happiness. All right, not bad. But this point over here, so the point B over here is on utility equals 40 or something. So it gives you more utility, and you're still spending the exact same amount of money. So between point A and B is better because it's giving you more happiness for the exact same price, for M dollars totally spent. You're just allocating it better between good 1 and good 2 to give you more happiness while still spending your fixed budget of M dollars. Now, point C over here would give you a lot more utility than 40, but unfortunately it's not affordable. It's outside of it's not on the red line. It's outside, it's above it, right? It's beyond it, so we can't afford it. So that's not even an option we're going to consider. And so, long story short, in economics, what they end up finding is that the place you want to be is over here, where the indifference curve is what we call tangent to the budget line. So it's where so let's say that's where utility is 50, right? So here, what we have at point C is it's still on the red line, but if you think about it, the only points that are on a utility curve above it, like so if we just focus in on this utility curve at, where it's tangent, the only other bundles even that are on a higher indifference curve are all to the up and to the right of this indifference curve. And all of those are unaffordable. They're not affordable to us because they're beyond the red line. So this C is sort of like this magical point where it's still affordable. It's on the red line, and it's indifferent as to all these other really expensive ones that we can't afford, right? And the only ones better than it are also not affordable. So that's why it's the best of all worlds, where it's still affordable, but there's no other point that gives us more happiness that's affordable, right? So that's why C is the best one. So really what you want to do is you want to set the slope of the budget. So here's what it means to be tangent. Tangent, if two things intersect, that means they have the same x and y coordinate. If two things are tangent, that means that they have the same slope as well. So in order to be tangent, we want the slope of the red guy to equal the slope of the indifference curve. The slope of the red guy, we knew from earlier. That's negative P1 over P2. That's the slope of the budget line. And so the slope, so all we need then is the slope of the indifference curve, the slope of the green or the blue indifference curves here. And if we had that slope, so notice, unlike the budget line, for the budget line, it's the same slope everywhere. It's a line. The slope is always P1 over P2. But for these indifference curve, it seems like it's getting like less flat as it moves on. So the slope is not a number. It's going to depend on the value of x1 and x2. And so the slope of a budget line, of the indifference curve, it has a special name, and it's not a single number, it's an equation. And so the slope of the indifference curve is called the marginal rate of substitution, the MRS. So the MRS is essentially the slope of the indifference curve of the IC. And essentially the way to interpret it is essentially it's how many units of x2 you're willing to give up. It's the number of units of x2 you're willing to give up to get one more unit of x1. That's what the slope means. So in order to be indifferent, in order for me to still like these the same amount, if the indifference curve has a slope of 4, that means that, all right, I'm willing to give up 4 bananas and get one more apple, and I'll still be on the same indifferent curve, meaning I'll be indifferent between those 2 points. So I'm willing to give up 4 for 1, if the slope is 4. That's all that means. And so the way to finally to solve it mathematically is using calculus. So the MRS, right, is, right, so the negative, right, because it's negative price ratio, so negative, and then the derivative of the utility function with respect to x1, so that's a partial derivative. It's a partial derivative with respect to x1 divided by the partial derivative with respect to x2. And that's also, the notation sometimes is also called marginal utility. So this is the marginal utility, meaning the derivative of utility with respect to good 1, divided by the derivative of utility with respect to good 2. So the main grand equation that you always see in econ, and so in economics that doesn't use calculus, they skip all this stuff and they just jump to the final thing, which is that the price ratio P1 over P2 equals MU1 over MU2. And here now we can see where that comes from. This is the price, the slope of the budget line, and this is the slope of the indifference curve, technically a negative, but on both sides so you can cancel it. And so when this slope equals that slope, they're tangent, and you've maximized your utility while being within your budget constraint.